Well, there's a couple of mysteries I won't be talking about tonight. So for those of you who, the dark side of the universe thought I was going to talk about the surge or something like that, I'm not talking about that. And I'm not going to talk about, we in the Midwest are a little bit, we're still trying to figure out how those Gators won. But go Gators. So just to put this in a little bit of context, astronomy is in one of the most exciting periods of discovery of all time. And I'll come back to this at the end, but I think an apt description of our exploration of the universe right now, and I don't mean the solar system, I mean the whole, darn universe, is that we know much and we understand less. And I'm going to tell you about two of the big mysteries, the mystery of the dark matter and the mystery of the dark energy. And what's really exciting and why it's really fun to be an astronomer right now is that we feel that these mysteries are within grasp. Within our reach. We don't quite know if they're within our grasp. We feel like we're going to be making measurements and doing experiments that could answer these questions. So there's some mysteries that you say, someday we'll figure those out. But with both of these mysteries, we feel like it's close. It's going to happen soon. And let me see if I can, I blank this out. Right. And can we adjust the lights a little bit? Or I guess can everybody see the screen? When you give an astronomy talk, you have such beautiful images. Although, it's only the first one, because the rest of them is going to be about the dark side. And so the dark side of the universe. So, when you think about astronomy, you think about beautiful pictures like this from the Hubble nebulae, and they really are quite beautiful. And when you think about astronomy, much of what we know about the universe is from the light that's given off by stars. And but it turns out, and sort of the most important point of this talk, is that the bright side of the universe accounts for less than 0.5%. And so I'm going to be telling you about the 99.5%. And so if there gets to be a rough spot where you say, why should I be interested? Well, it's the 99.5 to 0.5%. And the other thing that I'm going to be taught, dark matter and dark energy are very mysterious. And if I confuse you about both of them, I've caught you up to where we are. So if you get confused, that means you're learning. And one of the reasons they're mysterious is everybody knows. The reason I put star stuff in here is because Carl Sagan sort of immortalized that word or invented that word. We're made of the same thing stars are. The atoms in our body were made of stars. We're made of star stuff. The dark matter and dark energy isn't. And that makes it quite interesting. Okay, so let's wax poetic a little more about the visible side of the universe. This is a photograph that you paid for. It cost about $2 billion. And it was worth every penny of it. This was taken by the Hubble. It's called the Hubble Deep Field. I like to call it the Hubble Point and Shoot. Hubble stared for 2 weeks in one direction. And this is as far as you can see on a clear, I guess it was night. So this is very interesting. Most of the images here, this is just to orient you. So most of the images here, with one exception, this is a star. Everything else is a galaxy, distant galaxy, billions of light years away. These fuzzy little images are galaxies. Each galaxy has about 100 billion stars. There are 1,500 galaxies in this image. Now let me tell you the most amazing thing. We're not even to the dark side yet. The most amazing thing is this is 1/40,000,000th of the sky. And so if you want to know how many galaxies there are in the universe, don't ask me because I'm not very good at math. But you take 40, this is 1/40,000,000th of the sky. You take 40 million and you multiply it by 1,500, and I hope you get about 100 billion. There are a lot of galaxies. And this is literally as far as you can see. It's not because there was a defective mirror or it wasn't a good telescope. Is you're looking so far out in space that you're looking back to the time when galaxies were born. And of course, you can't look back any further because they weren't there to see. So one of the amazing things is, and we'll come back to this towards the end, is those of you who didn't think there was a time machine, astronomers have a time machine. It's a telescope. It doesn't quite work the way that everybody would want a time machine to work. It can't, but I'll let you figure that out. And we're going to be focusing literally on the spots between the galaxies, the dark side of the universe. Right, this is, when I went to Chicago, my mom said, don't let the bright lights fool you. Or no, what's that about? The dark side controls the universe. So just to remind you, stars are 0.5%. I'm going to talk about two weird things. Dark matter. Dark matter is a less weird thing, so I'll talk about it first. It accounts for 1/3 of the universe. Its gravity holds everything together, including our own galaxy. And I hope to bring it down to a level so it's not so mysterious. It's just made of particles. We don't know their names. They don't give off light. They're not atoms. Okay, so that's a little bit of a stretch. Oh, that's a big stretch? Uh-oh. You better tighten the seatbelts for the next one. And the other 2/3 of the universe, the bulk of the universe, is in something that is extraordinarily mysterious called dark energy. And it's diffuse. It's everywhere. Please don't use the word ether. I know somebody's going to use that word at some point. We don't completely understand it. Its defining feature is that its gravity is not attractive but repulsive, and it's pushing the universe apart, causing the universe to expand ever faster. And until we understand what the dark energy is and precisely how it's causing the universe to speed up, we can't say anything about the destiny of the universe. And I know everybody, the number one question on everybody's mind here is, what is the destiny of the universe? Right? Okay. Good. So let's start out. We're going to start out with the dark matter. So I'm going to talk for about 15, 20 minutes on the dark matter, and I'm going to walk you through it. So how can you know something is there that you can't see? That's kind of the, how can you, as I learned today, I had a wonderful day here at the Institute. One of the things I learned is that we have more senses other than our sight, so you can feel something. Although the feel here is a little bit different. So we feel the dark matter because its gravity, this is supposed to be our galaxy, its gravity is what keeps our star orbiting around the center of our galaxy. Its gravity is what keeps our star from just going off like that. So, just like gravity holds together our solar system, the gravity of the dark matter holds our galaxy together. It was actually discovered by a fellow named Fritz Zwicky, whose picture I'm going to show you in a second. And he stumbled upon it studying clusters of galaxies. So a cluster of galaxies is just a bunch of galaxies together. And what holds the galaxies together is the gravity of dark matter. So we know it's there because we see the effect of its gravity. I shouldn't have used the word feel, okay, so there's Fritz Zwicky. And he always gets a laugh. An extraordinarily brilliant scientist. You just had to ask him, and he would tell you that. In the modern parlance, he would have gone home, even from the laboratory, with a little note pinned to him, doesn't play well with others. And here he is describing, and you may have met people like this before, a spherical bastard. And a spherical bastard is a person, and it doesn't matter which side you approach them, they're a bastard. There's no good direction to approach them. So let me be serious. Look at all these. He wrote a lot of papers. He truly was a brilliant astrophysicist, but he was one of those people who was way ahead of his time. And dark matter, he's the first person, and I shouldn't say stumbled upon it. He really did it in a systematic way, but people didn't pay so much attention to him. You know, so you should be careful when you have your publicity photo taken. So how did he find it? And he was studying clusters. And let me show you how you would find a cluster in the sky. So this is a photograph of the sky. And in this one, let's say I was looking at this earlier, and I thought there were more than, I guess, well, those are stars. There might be a couple more stars. This is a little bigger patch of the sky. And most of the objects you see here are galaxies. And if you look carefully, you'll see right around here, there's a lot of galaxies together. You know, here they're more sparse, but here there's a bunch of them together. And Zwicky was the first one to classify and study these so-called clusters of galaxies. And what a cluster of galaxies is, it's just a region on the sky where you find many more galaxies than on average. And I'll show you the one in particular that he was studying because it's quite beautiful. And many of you may have heard the name. It's the Coma cluster. It's a mere 370 million light years away. Some of you may have visited it on your last vacation. And the Coma cluster has several thousand galaxies in it. And, well, you can't see all of them here, but it's quite big. And what Zwicky studied was the motion of the galaxies. So each one of these is a galaxy. Zwicky studied the motions. And he found, and this is a cartoon, and there's some inaccuracies, but he found not that they have little galaxies have arrows attached to them. He found that the galaxies are moving. He studied their motions. And what he found is they're moving quite fast. They're moving quite fast. And that's okay, and let's just follow this galaxy. So if there were no gravity acting on, if there weren't any gravity here, this galaxy would just go zooming off like that, and that galaxy would go zooming off like that. And if you look at the motions of the different galaxies, pretty soon there would be no cluster. They would all disperse. Everybody got that? Okay. Well, of course, Zwicky knew about gravity, and he was a very smart guy. And he said, okay, so it must be that the collective gravity of all the stars in all the galaxies holds the darn thing together. And so let me just walk you through this very quickly. So this galaxy here, or let's just take this one. It's trying to escape. It gets pulled back to the middle by the gravity of all the stars in all the galaxies. So it goes out a little ways. It falls back in. It overshoots. It goes out the other side, and so on and so forth. So he imagined, and we think he's correct, that the galaxies within a cluster do a little dance. They stay bound because of gravity. There was one tiny fly in the ointment. One tiny fly in the ointment. When you add up the gravity of all the stars and all the galaxies, because we know how stars work, and we know how much mass is associated with the light. We know how much galaxies weigh. You find out that the gravity of all the stars and all the galaxies misses working, falls short, I guess is the word I want, by a factor of 70. So it doesn't work. So there's sort of two ways you could go. I think Zwicky went the right way. One way you could go is to say, these clusters of galaxies are quite interesting. These are just chance superpositions. You got galaxies roaming the universe, and every once in a while, a bunch of them wind up in the same place, but that too will pass. If clusters of galaxies were rare instances, that would be a plausible explanation. We now know there's hundreds of thousands of clusters. That's not what happened. And so he posited that there must be additional mass here that didn't give off any light. And clever man called it dark matter. And literally, all it meant is matter that it doesn't even mean matter that doesn't give off light. It means matter that doesn't give any light we can detect. So dark matter. And so he wrote some paper. He coined the phrase dark matter. And so we talked. I think I have a slide later. So the gravity, that's what I just said. So, you know, what could the dark matter be? And but in the reception before, we were talking about, you know, could it be black holes? You know, after all, those are really cool. We now know it can't be black holes. They fail by more than a factor of 60. So we're going to talk a little bit about what it is. Here is a cluster of galaxies. It's not the Coma cluster. I can't remember which cluster. Maybe it is. I can't remember which cluster there is. There's a lot of clusters. Can't use all up your brain cells memorizing their names. And so in the 1980s, people started looking at clusters with other kinds of eyes to see if there might be things that you couldn't see with visible light. And this is what they saw with this cluster. Boy, I wish I could remember its name. And this is an X-ray image of this cluster. So it turns out that if you have X-ray eyes, anybody here have X-ray eyes? So one person can do this experiment at home. Of course, but I forgot to tell you which cluster. If you look at a cluster with X-ray eyes, they're just glowing in the X-ray. So this is, to the same scale, an X-ray image of this cluster. And the first thing that you notice with this X-ray image, which is quite interesting, is you can't see the individual galaxies. And so, in fact, what we learned in the 1980s is that these clusters are aglow with X-rays produced by hot gas. Hot gas. So clusters are filled with hot gas, and I mean just ordinary gas, hydrogen, helium, and so on and so forth. And this gas is so hot that the gas gives off X-rays. And this gas, there is a lot of this gas. This gas accounts for almost all the atoms in a cluster. There is 10 times as much mass in this gas as there is in the stars in the cluster. Now, some of you have been listening carefully, and you'll notice that 10 is not, I can't remember what number I said before, but 60 or 70. So there's a lot of hot gas, and in fact, that's where all the atoms are in a cluster, and we'll come back to that. But this is not the dark matter. Over the years, people have looked at various possibilities. Maybe it's faint stars. Well, we know our own galaxy. I'll come back to this. We know our own galaxy is held together by dark matter, and so we can use the Hubble to look for faint stars. There's not enough faint stars, so on and so forth. Now, when I was chairman of my department, I had a very tough provost. He was a lawyer. Very fair, but very tough. And I had to convince him that there was dark matter. And this was the image that convinced him. And by now, there is so much evidence for dark matter. But this is a very convincing, at least to a lawyer. Any lawyers here? Well, then maybe I should skip this slide. But I'll need it for something later. So this is a cluster whose name is 0024 plus 1654. And you can see the cluster galaxies. You guys are getting good at recognizing galaxies, right? And what's interesting in this picture, the galaxies are kind of orangish. But do you see these blue things? Really weird blue things? Well, they have a technical name. They're called faint blue galaxies. We're really good at naming. And it turns out that these faint blue galaxies are much farther away than the cluster. Much, much farther away than from the cluster. And so they're well behind the cluster. So their light has had to pass through the cluster in getting to us. And one of the weird things about these faint blue galaxies is, look at this one. It's shaped like a ring. And there's another one shaped like a ring, and another one, and another one, and another one. And then, let's see, look at this one. Boy, that one is really elongated. And, you know, there must be something going on here. And what's going on here, well, some people can just read it. It's a gravitational lens. So, according to Einstein's theory, gravity bends light. Okay, a lens bends light. When you look at something through a lens, you know, if it's a bad lens, it distorts things. And so what's happened is that this cluster of galaxies has acted like a lens, a gravitational lens, and this ring-like galaxy is just multiple images of the same galaxy produced by the bending of the light by the cluster. So this is not 5 different galaxies. It's just 5 different images produced by the fact that the light from this galaxy, which is actually closer to the center of the cluster, got bent. And then for galaxies that are further away, multiple images aren't produced, but distortions are produced. So this galaxy is not fundamentally cigar-shaped. It got sheared is the word that we used. And so you say, oh, well, that's very interesting. Well, it is very interesting because what one can do is, by understanding how gravity bends light, one can reverse the problem and say, oh, what distribution of matter would have given rise to these multiple images and these distorted galaxies? And so you can use this, one of the first tests of Einstein's theory, to figure out what the distribution of dark matter looks like. And this is what a scientist named Tony Tyson and his colleagues did. And so this is the coordinates on the sky, and up is mass. And just to orient you, these little spikes, those are the galaxies. So there are lots of mass at a certain position. And so you say, oh, well, I don't see the dark matter. Well, you don't see the dark matter because these spikes are more prominent. But if you see this gentle distribution of matter here, I mean, it's far less impressive, but that's where all the mass is in the dark matter. So we can image the dark matter. It really is there by using this technique of gravitational lensing. Last fall, I just have to show you this image because this was kind of cool. It's a picture that shows you that dark matter and ordinary matter are different things. And I want to walk you through this. It's kind of neat. Here's a cluster, which you actually saw before. Here's a smaller cluster. And it's called the bullet. Its phone number is 1E0657-56. You'll see in a second why it's called the bullet. So if you look at it with an optical telescope, it's not so impressive. If you look at it with the Chandra X-ray Observatory, if you look at it with X-ray eyes, so here is the big cluster, there's the smaller cluster. Now you're used to these false color pictures. This pink is the Chandra image superimposed, so that's the hot gas. And you say, well, just a second, I don't understand. You know, the hot gas is supposed to be, there should be some on that galaxy and there should be some on that galaxy. What's going on here? Well, what's going on here is that these two clusters collided, and they went through each other, and the gas in the two different galaxies collided and got left at the center of the collision, and the galaxies and the dark matter just went through one another, telling you dark matter is something different than the gas. And so here is where the hot gas got left. Here are the two clusters. And then if you use this gravitational lensing technique I was talking about, you can map out the distribution of the dark matter. So here's the hot gas, here's the distribution of the dark matter. And you can see the hot gas got left here and the dark matter is there. They got separated by this collision. So it's like a cosmic centrifuge. And to put it all together, so this is the hot gas. In blue is a representation of the dark matter. And you can see that they've clearly been separated. They must be made of something different. And so this is kind of reminding you of something near and dear to my heart, you know, particle physics, that, you know, you throw two things at each other, let them collide, and see what comes out. And in this case, what came out was the ordinary matter and the dark matter. They're different. Let me quickly bring the dark matter puzzle home. So here's Fritz. No one listened to him. This is a very famous astronomer named Vera Rubin. Actually, she was also served on the National Science Board for a number of years. And in the 1970s, she is the one who really brought this problem home. Clusters were a bit mysterious, and she brought this problem home because she showed the same thing is happening in galaxies like our own. So this is not our galaxy. This is actually Andromeda. How many people have seen Andromeda with the, yeah, good, with the naked eye? So we like to think of it as our twin. It's actually about twice as big, but that shows we have a good, healthy ego. And, of course, galaxies are made of hundreds of billions of stars. And the stars are moving around the center of the galaxy. And what holds, what makes them do that? Gravity, right? And this is what she measured are called rotation curves. And the rotation curve is just the speed of the galaxy, shown here as how far away the galaxy, sorry, not the speed of the galaxy, the speed of the star, shown as a function of how far it is from the center. And you're just supposed to take one thing away from this slide, which I'll demonstrate to you is weird, which is look at these stars. So this star way far from the center is moving at 250. This star even further from the center is moving at 250 kilometers per second. The rare star way out here, or typically gas clouds, are still moving at that speed. Does that seem weird to you? Yeah, the reason it seems weird to you is if all the mass were in here, as you get further and further away, gravity is getting weaker and weaker. Shouldn't the stars be moving slower? Otherwise, they're going to escape. That's good. Oh, you guys are really smart. Well, so you don't need this slide, because I was just going to show you a slide, the same thing for our solar system. So in the solar system, all the mass is in the sun. Okay? And if you make the same kind of plot, a rotation curve, here's, this is the hardest part of the talk. Pluto, Venus, Earth, Mars, Jupiter. Oh, I can't remember the planets. But what you see is she did not see this, which in the solar system where you have a big chunk of mass at the center, the planets or the objects that are farther away from the center are moving more slowly for exactly the reason that you all intuited, is the gravity's getting weaker. If they were moving fast, they would have escaped. Okay? And so what you infer from that, this is an optical image of our galaxy, which I took on an out-of-body experience. Actually, this is a real image. The reason we're able to take this, I bet you do this in Pensacola, is that we're not at the center of the galaxy. So we're out, we're not literally here, but we're, the galaxy is a bulge and then a disk, and we're out there. And so if you pan across the sky, don't you have pictures of Pensacola where you get a boat out there and you take a panoramic view? Okay, so it's the same thing of our galaxy. What's missing in this picture is the dark matter halo. So the amount of dark matter you need to hold the galaxy together is a lot, 30 or 40 times more than the visible matter. And here, I mean, this is not a picture of the dark matter. This is, you can see it's a poor representation. But what I wanted to show you here is that the dark halo of our galaxy is enormous. So the galaxy is tiny. The dark halo, not only in mass, is 30 times greater, but in size. Let's see what my next slide is. Oh, I want to go back. Let's go back to the Hubble Deep Field. Okay, so here's the Hubble Deep Field. And you know what it kind of looks like here is that galaxies are highly isolated. There's one here, there's one there. They're completely disconnected. Now go back to this slide. Galaxies have these enormous halos. In fact, our halo goes out to Andromeda. So in fact, our best understanding of the universe is that it is a web of dark matter decorated by stars. I don't mean that somebody went and, like a Christmas tree or something, but so this is a computer simulation of dark matter. And so it's not a real picture. It's a computer simulation of dark matter. And this is an enormous part of the universe, about 1 billion light years across. And so yeah, we're warming you up for the dark energy here. So the brightness here, the brighter it is, the more dark matter there is. You got it? Okay. And so you can see that the dark matter forms a web. There are filaments, and if we saw this in 3 dimensions, you'd see sheets of dark matter. And where there's more dark matter, the gravity is stronger, and more of the atoms fell in, and more stars formed, and it's brighter. Oh, now you understand the brightness scale. And so this is a nice metaphor for the universe, that it's a cosmic web of dark matter. And in the spots where there's an enormous amount of dark matter, enough ordinary matter accumulates that it forms a bright galaxy. And so if you can kind of look at this more as a Monet, what you see here is we now think of the universe as a web of dark matter decorated by stars and galaxies. And so whereas the stars and galaxies, if we call these the galaxies, look highly isolated, if you had a dark matter telescope, you could see that their dark matter halos are all interconnected. And in fact, some of you at the astronomers meeting is happening right now in Seattle. And I know at least one person came up to me and said, you know, did you hear about this 3D map of dark matter? Did anybody read that article? Oh, so all that work I spent studying that article is... Anyway, by gravitational lensing, we're starting to get pictures that confirm this cosmic web of dark matter. Okay. Now here's the fun part. I told you that the dark matter is not atoms. How do we know that? Well, we know that because Arthur Andersen told us that. You remember Arthur Andersen, the accounting firm that did such good work? So this is a puzzle anyone can understand. It's simple accounting. The total amount of dark matter that's needed to hold things together in the universe is 33% of something called the critical density. So I'll come back to the critical density, but just think of it as the number 33. The total amount of atoms in the universe is 4%, or a number called 4. Is there anyone here who doesn't recognize that 4 is less than 33? So there's just not enough atoms. Atoms only account for 4% of the stuff in the universe. The dark matter weighs in at 33% of the stuff in the universe. There is simply no way that 4 is equal to 33. Well, in astronomy, we used to do tricks like that, but we don't do that anymore. And so what that tells us is there's not enough ordinary matter to account for the vast amounts of dark matter. And I just quickly want to tell you, how is it that you know how many atoms there are in the universe? And because, I know, how did that slide get in there? Okay, well, I have to tell you a little bit about the history of the universe. It began as a can of quark soup. So this, in another lecture, I would tell you that this is basically a 2-scale model of the universe when it was very young. And it was a soup of elementary particles. And we can trace the history of the universe from this soup of elementary particles to where we are today. And that journey took about 13.7 billion years, and so I'm going to do it here for you in real time. I'll speed it up a little. So the quarks, everybody knows that neutrons and protons are made out of quarks, right? So when the universe was 100,000th of a second old, the quarks condensed into neutrons and protons. When the universe was seconds old, the neutrons and protons came together to form the nuclei of the lightest elements in the periodic table. We call this Big Bang nucleosynthesis, and when the universe was about a second old, it was a nuclear reactor. And then when the universe was about 400,000 years old, the nuclei that were around combined with the electrons that are around and formed the atoms. And then once we had the atoms, the rest was easy. We made stars and so on and so forth. So the two pieces of evidence that allow us to figure out how much ordinary matter is in the universe. In this nuclear reactor made helium. It made a heavy form of hydrogen called deuterium. Everybody's heard of deuterium? Okay. Made a light form of helium called helium-3, and it made lithium. And as best as I can tell, for the problems that we have in society today, it did not make enough lithium. But that's another lecture. And the amount of deuterium it made depends strongly upon the amount of atoms there were in the universe. And so a number of years ago, we measured how much deuterium was left over from the Big Bang, and that's how we pinned down this 4% number. You say, okay, well, that's really good. And I'm not going to argue with you because you're a scientist, but we have a double check now. And we can see the universe when the atoms are formed. And I'll show you a picture of that a little bit later. And we have an entirely different way to get at the amount of atoms in the universe. And guess what number we get? Yeah, we were hoping for 4. We didn't get, no, we got 4. So we have 2 different ways to get this 4% number. And so we're pretty confident. And there's actually a third way. So we're confident on that 4% number. I showed you the evidence for the dark matter. So 4 isn't equal to 33. What's the 33? What's that? Well, we went through a long list of candidates. Got all kinds of things here. Invisible axion. What's some fun? Shadow matter. Champs, chumps, crypto. We tried a lot of things. Black holes. So here's where we are today. In 1990, I made a slide, and I called this my moose diagram of dark matter candidates. And I'm going to talk about 3. 2 new particles that the elementary particle physicists had hypothesized. That means they don't really exist yet. We don't know whether or not they exist. One called the axion, one called the neutralino. I'll only talk about the neutralino. And then there was the neutrino. How many people have heard of neutrinos? Everybody's heard of neutrinos. You know they're ghostly, right? There's a lot of neutrinos in the universe. And the issue about whether or not the neutrinos are the dark matter is how much do they weigh. And in 1998, the big news was, and I bet you all remember this, is neutrinos have mass. Teeny tiny masses. And once we knew how much they weighed, then we could figure out how much of the dark matter they were. And guess how much of the dark matter they were? Not very much. So they account for more matter than stars do, but they're not the dark matter. So we are currently today, the 2 leading candidates are the axion and the neutralino. And let me just tell you a little bit about the neutralino. So how many people have heard of superstring theory? How many people understand it? Could you come up and explain it to me? So, superstring theory is the theory that unifies gravity and quantum mechanics, and it's the theory that made Brian Greene famous and all that. And one of the predictions it makes is that for every particle that we have found, there's a partner particle yet to be found. And so these superstring theorists say, look, our theory predicts, all these particles, we found half of them. So we're halfway there to verifying it. Any flaw in that logic? Okay. The neutralino is one of the particles that it predicts. And so this particle, if you go to Fermilab or if you go to the big new accelerator in Geneva called the LHC, you go into the control room and it says most wanted. And right under Osama bin Laden is a picture of the neutralino. And so this is a particle that we believe behaves very much like a neutrino. It's very, if it really exists and if it's the dark matter, thousands of them millions are passing through you every second. Of course, there are trillions of neutrinos passing through you every second. Weighs about 100 times, maybe 200 times what the proton does. And if we discover this would be fantastic. So number one, cosmologists like myself could say, yeah, we were the first ones to find it. We found it was the dark matter. We discovered that particle. And of course, if we produced it in the laboratory, that would give more credence to it. And of course, it would be the first evidence for superstring theory. And the axion is a similar story, although this is a story that it has its deep roots in Florida. So there's an experiment looking for axions that was designed by a physicist named Pierre Sakivi at the University of Florida. And so this is where I'm going to end the dark matter story. I mean, we have some of it. In fact, let me just go to the next slide here. So this is our accounting of the universe. So 4% atoms, about 30% dark matter. And I'm going to get to the dark energy, and that's where we're going to finish. The atoms, of that 4%, it breaks down like this. 0.5% of it is in stars. Most of it is in that hot gas that I showed you pictures of. So most of the atoms in the universe never got to be stars. And people want to know about black holes. Of these atoms, 0.0001% are in black holes. That's why the black holes failed miserably at being the dark matter. Then this exotic dark matter, as we call it, something that's not atoms, about 1% of it is neutrinos. Okay, well, we're looking for the full 30 here, and somebody is going to notice that these numbers don't add up. But consistency is the hobgoblin of small minds. Or I could have said they don't, it's rounding. They don't add due to rounding. And so we're focused in on axions and neutralinos. I'm a glass half full guy, even if I'm handed an empty glass. We feel like we're on the right track, that the dark matter is something other than atoms, because we've shown that some of it is neutrinos. And we feel like an experiment very soon, could be tomorrow, well, probably not tomorrow, but in the next few years, could identify that it's either axions or neutralinos. So we feel like this detective story is almost over. Started with Zwicky in 1935. We're not quite to show me I'm from Missouri. You'd like to see a bottle of the dark matter, but we're well on our way. Of course, there could be some big surprises. Let me now shift gears to the dark energy. The dark energy, that's what gets me up in the morning. I don't use it as a drug or anything like that, but it gets me excited. It's the puzzle I want to solve. It's a really big mystery. The story kind of starts in 1998 when Science magazine called its breakthrough of the year the discovery that the universe, the expansion of the universe, is speeding up and not slowing down. And so let me kind of work you up to 1998, and then there'll be a very short part telling you about dark energy, because we know very little about it. But let me tell you the puzzle. So let me remind you, you know my cartoon pictures of galaxies, and you know these funny little, that galaxies have arrows attached to them. So not really, but when we say the universe is expanding, we're referring to Hubble's discovery in 1929 that galaxies, he looked at other galaxies in the universe, and they're moving away from us. The big, and I have to put a pitch in for theorists here, is the big conceptual breakthrough was Einstein's general theory of relativity, and we're going to come back to the general relativity, and there will be a quiz on the general theory of relativity, that this is not, if you look at this picture, you might think that there was some explosion here and galaxies went hurling out into space. Much more interesting than that. Because Einstein told us that space is flexible. It's not absolute. And so what's really going on, if you can get your head around this, is space is expanding. And the galaxies are being carried along. And so way back when, the universe looked like this, and then a little bit later, after you put it through a copying machine and enlarge it, it looks like that. And so if you compare an early image with a late image, it looks like galaxies are moving away from you. Oh, this is fun. You might ask, are we at the center of the universe? I'm going to save this for the question time. But it turns out every galaxy thinks it's at the center. So it's kind of just like being at Harvard. And I'll show you how this works. So here I've done the enlargement for you. Here's a bunch of galaxies. They're further apart a little later. They're further apart a little later. And if you superimpose those three images, say on a particular galaxy, the one you live on, you see it looks like all the other galaxies are moving away from you because, in this time lapse, here it was a long time ago, a little bit later, a little bit later. And if you look at the same story for any galaxy, if you superimpose, you can do this experiment at home, any galaxy thinks all the others are moving away from each other. Okay, so you understand that. And so that means when we talk about the expansion of the universe, we can just talk about the size of the universe, that the expansion is just a scaling up. And so I bet everybody learned this diagram on their mother's knee. She said, here's the size of the universe versus time. I won't put in units because it'll only confuse you. And so here we have the universe getting bigger, like so. So it's getting bigger with time. And then your mother, and she said, when the universe was, that's the Big Bang, and it's getting bigger, it's expanding. That's what this chart means. And then she said the lines are droopy because the universe is slowing down, right? You all heard this story. So, a straight line would be the universe not slowing down, but it's slowing down. And then the big question, she said, is will it slow down enough so it will eventually fall back on itself? Or will it keep expanding, for example, like this one forever? Or is it the Goldilocks universe that keeps expanding and slowing, expanding and slowing, and it eventually halts infinitely long after the Big Bang? So that was the big question that astronomers wanted to learn. Which one of these is our universe? Which one of these is our universe? Well, how would you go about figuring that out? Well, you would use the fact that the telescope is a time machine. Now, this is the hardest slide. And I know I shouldn't have saved it for so late in the lecture. And as somebody said, you know, if he didn't understand at least 98% of this, I was in big trouble. So I hesitate to, but I'm going to put this slide in because this, so this is the famous diagram that, this is called the Hubble diagram. This is the diagram that made Hubble famous. And so what he did was on a graph, he plotted the velocity or the speed at which galaxies were moving away from us versus their distance. And he found a straight line. And you could see that from an earlier slide that I had. Oh, I shouldn't have done that. Right? Notice the galaxies are farther away or moving faster. So you all knew that. So this is the famous Hubble diagram. And now here's the part where I just want you to concentrate for about 30 seconds. So when we look at very distant, and if we could look at measure galaxy distances and velocities the way they are today, which we can't, we obviously can't do that, you would just get a straight line because of Einstein's observation that the expansion of the universe is just a scaling up of space. Because the telescope is a time machine, when we look at very distant galaxies, we're looking back in time. And so we're looking at them as they were a long time ago. Okay, now here comes the hard part, and it's actually not that hard. If the universe is slowing down, that means that we're seeing, let's say, this very distant galaxy right here, a long time ago. This is the speed it's moving today, but if the universe were slowing down, if we measure its speed a long time ago, it would be faster. And so we would actually measure it to be up here. And so the trick is that if you measure very distant galaxies and put them on the Hubble diagram, you'll be able to measure how much this curve bends from being a straight line, and the bending will tell you how much the universe is slowing down. And I'm not going to embarrass you to, did everybody get that? Yeah, you all got that. So now I'm going to show you the data, and this is, I'm not going to show you real data because it's hard to see the effect with real data. So these are, this is the funny symbol that we draw for data points. And so here is what made Hubble famous, that there's this linear relationship. And the points are below the straight line, not above. Now, above means slowing down. So what does below mean? Oh, you guys are really good. Speeding up. And so it was very exciting. I mean, it was unexpected and very exciting. And it means that the universe is speeding up. Oh, I won't tell you how it was done if somebody asks me. And it made the cover of Science magazine because this was completely unexpected. It's a funny scientific story. You know, science is really wonderful. There were two groups that were trying to make these measurements. And the two groups, they only agreed on one thing, which was the other group was stupid and incompetent. And each group only had one goal, which was to get the different answer than the other group because they're, you know, read bullet number one. And the biggest surprise of all was not that the universe was speeding up, it's that they got the same answer as the other group. And of course, in science, we like to have independent measurements. We like two groups that, well, you know, they should be nice to one another, but we like two groups that are competitive. Competition is good, right? And so in 1998, they discovered the universe was speeding up. And you know, I'm gonna, because I've already stretched your mind, I'm gonna skip some of this. We had some confirming evidence that involved measurements of the cosmic microwave background, but I'm actually gonna skip this. So we got confirming evidence. other measurements came to the same conclusion. You know, but in science, we worry about discoveries that are too good to be true. And Sir Arthur Eddington, this is a great quote. This is a wonderful quote. "No experimental result should be accepted until confirmed by theory." How many people are offended here? And actually, this is a wonderful quote because it takes the experimentalists a while to understand the quote. It's kind of like telling Polish jokes to Polish people. You have to do it slowly. But once you do, you understand that this is kind of a fundamental tenet of science. Science is not just a book of facts. It's understanding. And if there's certain facts you can't understand, they may not actually be facts. And so this is the segue into, so how do we understand this? Is this too good to be true? You know, is this such a crazy result that maybe it's not true? And the answer is no. And here's how we understand it. Cosmic acceleration, that is the speeding up of the universe, is driven by the repulsive gravity of dark energy. And this is my last slide. Is there anyone who doesn't understand that? Oh, somebody said my line. So let me explain that. This is where it starts getting really interesting. I'm going to explain the puzzle, and then we'll wrap up here. So it turns out that gravity can be repulsive. I don't mean the learning about gravity. I mean that gravity can be repulsive. Now that is deeply mysterious because if there is anything that you remember about gravity, what's its defining feature? It's attractive. Well, it turns out that according to Einstein's theory of relativity, gravity can be repulsive. Now, the stuff that has repulsive gravity is very, very weird, and I named it. So this is my great contribution to dark energy, is I named it. So you know, before you can start talking about something, you have to give it a name. Because you can't always refer to it as the stuff that has repulsive gravity. So according to Einstein's theory, it is possible for very weird substances to have repulsive gravity. And as a class, we call that dark energy. And let me tell you about something that has repulsive gravity. Let me tell you about something that almost could be the answer. This is now the Zen part of the talk. And it has to do with quantum nothingness. And so we start out with the question, what is nothing? Well, according to quantum mechanics, nothing is not nothing. Nothing is something. Still with me? So according to quantum mechanics, the vacuum is not empty, but it's filled with particles living on borrowed time and borrowed energy. And I must have spent too much time in Washington, but it seems to me in 2004, one of the candidates, their economic plan involved living on borrowed time and borrowed energy, but I could be wrong. So according to quantum mechanics, you can borrow some energy, and an electron and its antiparticle, a positron, can pop out of the vacuum. Before the accountants come, they disappear. This is real. The effect of, we call these virtual particles, the effect of these virtual particles has actually been measured in the laboratory, and at least 2 Nobel Prizes for these measurements have been awarded. So this is a real thing. So the vacuum really is filled with virtual particles. So this is the hard part. The easy part is, and I'm not going to even try to motivate it, it turns out that if these virtual particles have mass or weight, their gravity is repulsive. And I kind of just say, why not? I mean, if you've come this far with me. So this is the kind of stuff that has repulsive gravity. And so you might say, well, this is starting to sound quite good. So you can prove mathematically that the energy of the quantum vacuum, we call this vacuum energy or quantum vacuum energy, has repulsive gravity. And so in all situations with gravity, the total amount of repulsion or the total amount of attraction depends upon how much it weighs, right? So the big question is, how much does nothing weigh? I told you this was the Zen part of the talk. And, you know, when we theorists calculate how much nothing weighs, we get an answer that comes very close to giving the right result. That is, the right speed up for the universe. It's within a factor of 10 to the 55. I apologize for those of you who don't know scientific notation. That means we're only off by a factor of 1 with 55 zeros. And, OK, it's not very close at all. OK, so this is what we really like, what theoretical scientists really like. We have a very big puzzle. And these very big puzzles, we know that the answer will be a crazy idea. It's not going to be, you know, Professor Turner and your calculation of how much nothing weighs on page 22. There was a 2 that should have been a pi, and everything works out. That's not going to happen. And so to resolve this puzzle, it's going to require a crazy idea. And that's where, you know, theorists get excited. And this is, because I know you're going to be able to find my email address. Not every crazy idea is a solution to a profound problem. So some crazy ideas are just plain crazy. And the crazy idea could be to explain how nothing weighs so little. Right? It could be that, you know, the crazy idea just explains why. Or the crazy idea could be, well, you know, nothing weighs nothing. And in fact, I claim that as my theorem. I think if it turns out quantum vacuum energy weighs nothing, we're going to call that Turner's theorem. And then, what is the dark energy? So I'm going to show you 2 ideas, and then I will be done. And it's kind of a father-son thing. In 1998, I think my son was... Yeah, I did have a son in 1998. And he was 5 then. And we both like to make transparencies. And so I sat him down at his little desk, and I said, will you please draw me a picture of dark energy? And there it is. And I think that his idea of what dark energy is competitive with every other idea that I've heard. But I could not be outdone with my son. You'd have to know him. It's a competitive father-son thing, and we go at it. And so here's my crazy idea. There is no dark energy. The guy who invented dark energy is telling you, no, there's no dark energy. That we're seeing a new aspect of gravity. And let me tell you what this new aspect of gravity is. And I'm not saying this idea is right. All I want you to do is accept that it's crazy. OK, so, and the idea is that an empty universe undergoes accelerated expansion. Well, how would that work? Why would that make everything work? So here's how it works. The universe is expanding. The matter's getting diluted. It's getting emptier and emptier. And all of a sudden, it gets empty enough that it starts accelerating. So this is a very crazy idea. My colleagues and I have tried to make mathematical equations, write down mathematical equations that make this idea work. Our equations were interesting enough to get us in the New York Times, but they weren't interesting enough to work. Anyway, so we're trying to figure out what may... Oh, and then Alan Greenspan. Does anybody remember Alan Greenspan? This is an old slide. So those of you who remember, I mean, he wanted to get in on this, and he claimed he predicted it. And this is sort of this is an inside baseball joke, because some of you who know about the beginning of the universe know about something that we call inflation. That early on, we think the universe went through a speed up. And so Alan Greenspan claims that he wrote a paper a long time ago saying mild episodes of inflation are unavoidable. And he claims that we're just going through this accelerated expansion period is just a mild episode of inflation. Oh, I want to talk about one other thing, and then we're done. So here is the picture that your mother told you about on her knee. So hello, she said droopy lines. So, you know, was your mother wrong? No, mothers are never wrong. As you fell asleep, your mother said, of course this picture assumes that there is no dark energy. Once you put in dark energy, all bets are off. And so here's what we know the picture looks like now. I didn't tell you that we know... Anyway, here's what the picture looks like now, is we are speeding up. It's not a droopy line, but the size is accelerating with time. But we don't know what the outcome's going to be. It could continue to speed up, And in fact, you know, I mean, not only did this not work on Congress, it didn't even work on Ken Ford. If the universe continues to speed up the way it's going now, in 100 billion years, all the galaxies are going to be so far away that the sky is going to be dark and we can't do astronomy, and so now is the time to spend money on astronomy. It could be that Alan Greenspan was right, that this is just kind of a passing phase. The dark energy will decay, and we'll go back to this slowdown phase. Or it could be that the dark energy is so mysterious that it leads to a recollapse of the universe. So the whole destiny question is wide open. Oh, nobody wants to hear about the Nancy Kerrigan problem. Oh, yeah, somebody does. So what's interesting about this is, and this is a really good slide to talk about these two, the battle of the dark titans. Dark matter, dark energy. Dark matter, that shaped the universe. It made the structure. Dark energy is causing the universe to speed up. It turns out in the past, dark matter was more important than dark energy. So this is a slide that shows time and the amount. And as time went on, dark matter got more dilute and less important. And dark energy, we think its density stays about constant. And so if you put this together, it means in the past, dark matter dominated, now dark energy is dominating. So here this is when the structure was formed, this is when the universe is speeding up. And so there's a why now problem. You all remember Nancy Kerrigan and getting whacked on the knee and why now? So we have a why now problem. Why is it about 4 billion years ago that we switched over from the dark matter being dominant to the dark energy? And this is the great thing about science. This could be a completely inconsequential question whose answer is, it's just a coincidence, or it could be, you know, the big clue. Oh, I think this is a really, I already told you this. This problem gets me up out of bed in the morning. And I'll skip that slide. And I'll just remind you, we know what the universe is made out of. It's 0.5% stars, mostly 1/3 dark matter and 2/3 dark energy. And that's kind of a metaphor for what I said at the beginning. And we know a lot about the universe. You know, I didn't get a chance to talk about inflation, but I alluded to it. We know that the universe began with a hot Big Bang. I better use this one. We know about dark energy, cosmic acceleration. Baryons is a fancy word for atoms. So we know a lot about, oops, oh, I didn't want to do that. We know a lot about the universe. And the big thing today is to put this picture together. And that's, in some ways, the most exciting time in science. It's the most exciting science. If you don't know anything, you know, then you're just sitting around BSing. If you know everything, if you're down to the 15th decimal place, it's less exciting. When you got all the puzzle pieces in front of you, and then you're trying to put it together, that's very exciting. So I asked my daughter, and she's really smart, smarter than my son and I. So I asked her, you know, okay, Rachel, you're so darn smart. So what is it? And she said, Daddy, it's an elephant. So in cosmology today, we're like the six blind cosmologists. You know, we're feeling different pieces of this elephant. You know, we got all these facts, and we're trying to put it together in a big story. And two big mysteries that I told you about: dark matter and dark energy. And the reason we're excited is, the reason we think things are within grasp is, here are some of the experiments that are going on and will go on. At Fermilab, they're trying to make the dark matter particle. There's a big new accelerator in Geneva called the LHC, which will turn on this year, more powerful. We hope to have a telescope dedicated to studying dark energy. We hope to have a ground-based telescope. This is a space telescope, ground-based telescope, studying dark energy. This is an experiment looking for the dark matter particle. So stay tuned. Thank you very much. Now, I think we have time for a couple of questions. You've got to remember the rules. Easy questions, and you can't ask them until the microphone comes. Sir. But remember, you got to get a microphone first.
Harold Loesch. I couldn't understand at all what I was listening to, but it was interesting. But I had some thoughts. One of the thoughts was when the astronomers found things that didn't fit their theories, they were looking for answers, and maybe they invented dark matter and dark energy in order to try to fit their theory, and now they're spending their time trying to fit dark matter and dark energy so that they will answer the questions that couldn't be answered before.
Well, I think that you just described how science proceeds very accurately. And guesswork is very important. When you get a puzzle, you got to make a guess, and sometimes it involves something new. And the key feature of science, which you also encapsulated, was that if you make a guess, if you invent a new idea, if it's science, it's got to be testable. So you can't just say, oh, yeah, there's this stuff out there, blah, blah, blah. So, and I would take the neutralino, the dark matter, as an example. So we think it's a new form of matter. Okay, that's a great idea. That's fair. Let's test that idea. And so we're testing it now by trying to make the dark matter at a particle accelerator, by trying to detect it with, I didn't talk much about that, with an ultra-sensitive detector. And that's how the process of science works. And I think that's what makes it so exciting, is when you go to school and you read textbooks about science, I think everybody, Ken and I and all the others, the first thing you think is, well, everything is known. It's all in this book. There's nothing yet to be discovered. But there is so much yet to be discovered. And that's what's fun, is inventing the new ideas, and most of them are wrong. The dark matter isn't black holes. We ruled that out. We narrowed it down to 2 ideas, and we're going to test those ideas. And I can see you're the guy from Missouri. And if it's neutralinos, I know you're going to ask for a bottle. And that's what we're trying to do now, is bring back a bottle of neutralinos. And sometimes in science, when you work on the really, really big puzzles, the solution that you put forward sounds like a fairy tale. It absolutely, quantum mechanics sounded like a fairy tale. But let me just remind you of the ending of this quantum mechanics fairy tale. 40% of our GDP is tied to quantum mechanics. So that fairy tale had a very good ending. How about over here in that corner?
When you were describing all this, it seemed like you were describing a cosmic living organism. When you're putting this all together, you're talking about the dark energy and the dark matter interconnected, you know, the string theory and so on and so forth. Have you ever considered that this is within that realm?
Well, I'm not sure I would call it an organism, because, you know, right now the physical sciences are competing for their dear life with the biological sciences. So we don't want to go the next step forward and say that. But, you know, in science, what we're always looking for is a coherent understanding. You know what the word cosmos means? It doesn't mean billions and billions. It means order. And the amazing thing about the universe is the order that we see in it. You know, from the idea that there are laws of physics. You know, the sun rises every day. I guess it does. And you know, we can predict things. And so a guiding principle in science has been, number one, the universe is governed by laws. That I could give a whole long thing on our evidence for that everywhere the laws are the same. And that the laws are knowable, and that's worked out pretty well. We know most of the laws of physics. And that the laws and the story are pretty simple. And I'm not saying that we know that for sure, but we've gone an awful long way on that. And when you look at what we know about the universe, Big Bang beginning, you know, cosmic nuclear reactor, we've been able to put together a fairly simple story, that the laws of physics that govern the beginning of the universe are the same as the ones that we have today. And so there's no guarantee that at the end of the day the picture is very simple. But so far, it has been. It may be that eventually it turns out it's just really complicated. Yes, right.
Hi, my name is Laura. Thank you very much. With dark energy, the universe is speeding up.
The expansion of the universe is speeding up.
I've heard that before, and I can theorize about what that means on a day-to-day basis.
Not without a license from me.
But, you know, you hear all different kinds of things, but how does that show up in our day-to-day lives? I mean, is that cell phones? Is that, you know, I don't mean
Yeah,
in
I don't
particular.
think it shows. I think Ken, no, it doesn't show up in our day-to-day life.
It doesn't.
The expansion of the universe, our galaxy is not expanding. If you would actually, one of the great technological challenges in cosmology is to actually make a measurement to see a galaxy move. So we've never seen a galaxy, sorry, we haven't seen the distance change. I mean, we see that we can measure that it's moving away. We can measure speed, but we haven't measured the distance. And that's because, just to give you a sense of things, in 14 billion years, which is a long time, the universe will double in size. And so that means in a year, the change in size of the universe is about 1 part in 10 billion. And so to actually measure just the expansion of the universe, we haven't even got to the speed up. You'd have to measure the distance to some object, some galaxy, some distant galaxy, to an accuracy of 1 part in 10 billion. So I think in terms of your ordinary life, you know, the expansion of the universe is not affecting global warming. It's, you know, any of that. But it seems to me that you know, we all want to know, how do we get here? Where are we going? That's what's exciting about cosmology. There's a question. Why don't you hand the microphone to the woman? Oh, it already got taken away. Just like the O'Reilly
This
effect.
might be a foolish question, but in the future, when we learn more about the dark energy, you think it might be possible for space travel to hook into that somehow and get to other places in the universe?
One of the, I have no idea. Oh, theorists hate to say things like that. But, you know, where scientists go wrong is when they say never. And so, well, then how can you never say never because you're, okay, but Ken can help us with how you can never say never. And I come back to quantum mechanics. And so how many people in this room think quantum mechanics is esoteric and mysterious and hard to understand? And just imagine now, 80 years ago, it has to have been at least as esoteric or more esoteric than dark energy. And I was really serious. When I said, this was not a joke, when I said 1/3 or 40%, I don't know the exact number, of our economy is based on quantum mechanics. What I meant is we live in an information society. Quantum devices create information. They store information. They manipulate the information. They move it from A to B. And here is something that was so esoteric that you could not, I don't think anyone could have imagined that quantum mechanics would have any practical use. And so, you know, in terms of dark energy, I just wouldn't want to, my tendency is to say, no, nah, it's, you know, too weird, it's too diffuse, you'll never be able to, so I don't know. But right now, it's just the biggest exciting puzzle out there. Here, for 300 years, we thought gravity was repulsive, and now we find out, sorry, attractive. I was thinking ahead 300 years. But you never know. That's the great thing about science. But if history is any guide, when we discover things about how nature works, people are very clever to take advantage of those things to make life more comfortable for all of us.
Okay, 2 more questions.
Yeah, don't maul.
Thank you for a great lecture. Is it possible that we're doing ourselves a great disservice by using the word dark, because dark has got a connotation kind of a bad connotation. Couldn't dark energy simply be energy that with our modern technology we cannot perceive? We just haven't got the perception with our technology to see it. It's there, it's positive, it's wonderful. We just can't, with our technology, see it right now or measure it.
Well, scientists are not very good at naming things. And, you're asking me to criticize something I named, so a little self-credit. As long as I don't have to go out and work in the fields or something like that, I guess we're not in China. You do need to have a name for something, and, the names are always crummy. But what it was supposed to encapsulate is it's like energy, and that's technical. It's more like energy than matter. So dark matter, we think, is particles, that you can break the dark matter into particles. Dark energy, you can't. It's more like a diffuse form of energy. And dark is just a cool word. We did focus group things, and, it was kind of a nice yin and yang with dark matter and dark energy. And the goal, of course, is that dark matter, the word will go away, and we'll put the proper particle name there. And with dark energy, the goal is that the name will go away. But what's wonderful about names is that the history of I come back to science being organic and exciting, and so the names kind of tell you some of the history, the struggles, that people didn't really understand things very well. And often the names are misnomers. And so there's a particle that some of you may know of called the mu meson. The muon, anybody know the mu? It's not a meson. But when they discovered it, they thought it was. And so it's cool that it keeps the name the mu meson because it encodes some of the history. Okay, we're down to the last question, and it better be an easy one. Were you choosing it, Ken? So let Ken, yeah, back there.
Hi, thank you for the lectures. It was terrific. Going back to talking about how the existence of dark matter was originally deduced by seeing in what direction galaxies were moving. You kind of touched on this previously in one of your other responses to a question, but since, of course, we've only been able to see galaxies for such a ridiculously recent amount of time, how do we know that they're moving in one direction or another, and how fast they're moving? Is it only through redshifts, or is it other ways?
The redshifts are the Doppler effect, so it's the same way you get speeding tickets, right? So they got a radar gun. It's not a radar gun here, but when something is moving, the light that it emits, if it's moving away from you, what you detect is at a lower frequency, or it's redder. And if it's moving towards you, I hope I said this the right way, it's at a higher frequency. So it's the famous Doppler effect that makes a train going by. And I know you're going to ask me, but I drew the arrows.
Vector from, how do you know it's actually going in one direction instead of just a slower rate of
So
change?
the easiest way to measure velocities is away from you or toward you. And so when I put that slide up, I said there was a simplification here. There was a mistake in that slide. And so he didn't measure the velocities across the sky. Although for nearby stars, we can measure the velocities across the sky by looking at them today and then 100 years later, and they actually have moved. But for galaxies, you can't do that, and that was the cheat in that slide, and you caught me. So you get the prize.
Yeah. That's a good last question. Thank you.
Thank you very much. Well, there's a couple of mysteries I won't be talking about tonight. So for those of you who, the dark side of the universe thought I was going to talk about the surge or something like that, I'm not talking about that. And I'm not going to talk about, we in the Midwest are a little bit, we're still trying to figure out how those Gators won. But go Gators. So just to put this in a little bit of context, astronomy is in one of the most exciting periods of discovery of all time. And I'll come back to this at the end, but I think an apt description of our exploration of the universe right now, and I don't mean the solar system, I mean the whole, darn universe, is that we know much and we understand less. And I'm going to tell you about two of the big mysteries, the mystery of the dark matter and the mystery of the dark energy. And what's really exciting and why it's really fun to be an astronomer right now is that we feel that these mysteries are within grasp, within our reach. We don't quite know if they're within our grasp. We feel like we're going to be making measurements and doing experiments that could answer these questions. So there's some mysteries sort of immortalized that word or invented that word. We're made of the same thing stars are. The atoms in our body were made of stars. We're made of star stuff. The dark matter and dark energy isn't. And that makes it quite interesting. Okay, so let's wax poetic a little more about the visible side of the universe. This is a photograph that you paid for. It cost about $2 billion. And it was worth every penny of it. This was taken by the Hubble. It's called the Hubble Deep Field. I like to call it the Hubble Point and Shoot. Hubble stared for 2 weeks in one direction. And this is as far as you can see on a clear, I guess it was night. So this is very interesting. Most of the images here, this is just to orient you. So most of the images here, with one exception, this is a star. Everything else is a galaxy, distant galaxy, billions of light years away. These fuzzy little images are galaxies. Each galaxy has about 100 billion stars. There are 1,500 galaxies in this image. Now let me tell you the most amazing thing. We're not even to the dark side yet. The most amazing thing is this is 1/40,000,000th of the sky. And so if you want to know how many galaxies there are in the universe, don't ask me because I'm not very good at math. But you take 40, this is 1/40,000,000th of the sky. You take 40 million and you multiply it by 1,500, and I hope you get about 100 billion. There are a lot of galaxies. And this is literally as far as you can see. It's not because there was a defective mirror or it wasn't a good telescope. You're looking so far out in space that you're looking back to the time when galaxies were born. And of course, you can't look back any further because they weren't there to see. So one of the amazing things is, and we'll come back to this towards the end, is those of you who didn't think there was a time machine, astronomers have a time machine. It's a telescope. It doesn't quite work the way that everybody would want a time machine to work. It can't, but I'll let you figure that out. And we're going to be focusing literally on the spots between the galaxies, the dark side of the universe. Right, this is, when I went to Chicago, my mom said, don't let the bright lights fool you. Or no, what's that about? The dark side controls the universe. So just to remind you, stars are 0.5%. I'm going to talk about two weird things. Dark matter. Dark matter is a less weird thing, so I'll talk about it first. It accounts for 1/3 of the universe. Its gravity holds everything together, including our own galaxy. And I hope to bring it down to a level so it's not so mysterious. It's just made of particles. We don't know their names. They don't give off light. They're not atoms. Okay, so that's a little bit of a stretch. Oh, that's a big stretch? Uh-oh. You better tighten the seatbelts for the next one. And the other 2/3 of the universe, the bulk of the universe, is in something that you say, someday we'll figure those out. But with both of these mysteries, we feel like it's close. It's going to happen soon. And let me see if I can, I blanked this out. Right. And can we adjust the lights a little bit? Or I guess can everybody see the screen? When you give an astronomy talk, you have such beautiful images. Although, it's only the first one because the rest of them is going to be about the dark side. And so the dark side of the universe. So, when you think about astronomy, you think about beautiful pictures like this from the Hubble nebulae, and they really are quite beautiful. And when you think about astronomy, much of what we know about the universe is from the light that's given off by stars. And but it turns out, and sort of the most important point of this talk, is that the bright side of the universe accounts for less than 0.5%. And so I'm going to be telling you about the 99.5%. And so if there gets to be a rough spot where you say, why should I be interested? Well, it's the 99.5 to 0.5%. And the other thing that I'm going to be taught, dark matter and dark energy are very mysterious. And if I confuse you about both of them, I've caught you up to where we are. So if you get confused, that means you're learning. And one of the reasons they're mysterious is everybody knows. The reason I put star stuff in here is because Carl Sagan, extraordinarily mysterious, called dark energy. And it's diffuse, it's everywhere. Please don't use the word ether. I know somebody's going to use that word at some point. We don't completely understand it. Its defining feature is that its gravity is not attractive but repulsive, and it's pushing the universe apart, causing the universe to expand ever faster. And until we understand what the dark energy is and precisely how it's causing the universe to speed up, we can't say anything about the destiny of the universe. And I know everybody, you know, the number one question on everybody's mind here is, what is the destiny of the universe? Right? Okay. Good. So let's start out. We're going to start out with the dark matter. So I'm going to talk for about 15, 20 minutes on the dark matter, and I'm going to walk you through it. So how can you know something is there that you can't see? That, you know, that's kind of the, how can you, as I learned today, I had a wonderful day here at the Institute. You know, one of the things I learned is that we have more senses other than our sight, so you can feel something. Although the feel here is a little bit different. So we feel the dark matter because its gravity, this is supposed to be our galaxy, its gravity is what keeps our star orbiting around the center of our galaxy. Its gravity is what keeps our star from just going off like that. So, you know, just like gravity holds together our solar system, the gravity of the dark matter holds our galaxy together. It was actually discovered by a fellow